Shall we start? Yeah. In fact, problem of teaching is one side. Problem of learning is another side. In the classes, sometimes students will come and rectify, correct, right? Actually, I used to actually when I was young, I used to write on the board, right? This as I'll write as I write in the notes, right? People tell don't write like that, right? We cannot write right from that board. We cannot infer. So you have to write the letters separately, right? Don't combine write, but don't collectively write. Like that, people are telling, right? So after some time, I learned from the students that I have to write separately and on bold, right? Actually, I have to write boldly, right? I have to write little on the high size, right? Only then can they really write. So in fact, I'm really thankful to her. The real problem, right? I was going, this window, that window, nothing is shown. Right? Fine, very good, thank you. Right? Fine. Now we are going to see the hydroscarcity problem. Hydroscarcity is very similar to the autocorrelation problem, right? Only difference between the hydroscarcity and autocorrelation problem is autocorrelation problem will come mainly for the time series, right? Time series data. Hydroscarcity problem will come in the cross-section data, right? So this is a very big difference, right? Implication is the very same, right? Whatever implication we had for the autocorrelation will come for the hydroscarcity also, right? So what are the problems? It will not affect the estimation of the parameters or coefficients, right? Estimation will not be affected, but the estimation of standard errors will be affected. Estimation of standard errors will be affected. So again, the problem is overestimation or underestimation of standard errors. So the problem will come only in the estimation of standard error, and so it will affect the t values. So that is the big problem, right? So whatever I said for the autocorrelation holds true for the hydroscarcity also, right? So it will be inefficient, right? Actually, there is a problem of wrong inference. There is a risk of wrong inference. Type 1, type 2 error can occur, right? So this is the problem. How would you diagnose? How would you diagnose this issue? The main diagnostic problem, the diagnostic tests, right? Very prominent diagnostic tests are Bruce-Pagan and White's test, right? Both are LM tests. LM tests are it is based on auxiliary equations. It is based on auxiliary equations. You will run the first regression. So this is the main regression, right? This is the main regression. Main regression. After that, you will take the residual value and you will take some proxy for residuals as the variance. What is the heteroscedasticity problem? Hetero means what? Different. Skedasticity is the variance, right? Different variance, right? So for each observation, you will have some error term. The error term will have different variance, right? If you ask me, sir, I have one observation, observation number 1, I will have only one residual, but we are handling the sample. The sample can change. The sample can change, right? We know the possibility of changing the samples, right? If you have got 10 population, if you take 2 out of it, there are 10 C2 times we can draw samples, right? So there is possibility of different sampling. In such cases, this U for the first observation will change, right? You can find variance for it, right? So for each of the observations, such possibilities exist, and for each of the variance, right, for each of the residual, you'll have the variance. Those variances have to be same, right? Actually, in fact, this can be represented this way. Yeah. We know the heteroscedasticity definition. Hetero means different. So this is the usual diagram given, right? This is heteroscedasticity. This is homoscedasticity, right? Here the variance, actually this variation is shown for the outcome variable. That holds true for the residual variable also, right? So what you see here, right? Actually here the savings for each of the income, savings are fluctuating among different income class groups, right? The same can be expressed for the residuals, right? So you'll have different variance, right? That situation is known as heteroscedastic situation. Otherwise, homoscedastic situation is that one, right? For all the observations, you have the same variations, right? Same means homo. Scedasticity is variation. Same variation, different variation, right? That is the difference. Actually, the OLS models assume homoscedasticity, right? In reality, there is a possibility of heteroscedasticity, right? If there is a heteroscedasticity, right, this will affect the estimation of standard error for the coefficients, right? Standard error for the estimates, right? That is the problem, right? This many tests are available, right? Theoretically, this many tests are available. Very prominent tests are White's test and Bruce-Pagan test, right? So it's very simple. I just asked, right? Actually, I just asked how to do a test, right, in R. Heteroscedastic test in R, right? So Bruce-Pagan test is there. For the autocorrelation, it was Bruce-Godfrey test. This is Bruce-Pagan test. Forget about everything. Actually, I'm not going to run it because the same old things are going to be repeated, right? So LM test, there is a function called BP test. Run the regression model. Keep that model as some, you save it as a model here, right? You just put BP test. Actually, first, open or load the LM package, LM test package, then type the BP test function, right? Within that, you put the model, right? That will get you the results, right? If you run actually, right? Actually, since we have the data, we'll read that data and we'll run it as quickly as possible, right? Let us not spend too much time because we can do some work on autocorrelation, multicollinearity also, right? We have to cover it in 1.5 hours, right? Actually, I was told you will prefer to leave by 4:30, right? I will finish it. Okay. First, now I'll take the data as usual, right? This is the heteroscedasticity data, right? I'll just take this data. I'll just save this sheet as CSV file, right? HC1. I'm going to save this as HC1. HC1, right? HC1, save as CSV file. CSV files are text files. CSV files are text files. It can be read as text files also, right? Your notepad can also read CSV file. Yeah. So data is read into, data is saved as HC file, HC1. Will not save. Save as already there. Okay. Somewhere that HC1 is there. It's here. Okay. I'll read the file now. I can use this code. All I need to do is to change that file. That's it. This is HC1, right? HC1. Right, HC1. Otherwise, everything is the same. Right? I'm not going to change anything. I'll send this file to you through WhatsApp. You may take this file from him. Okay. I have sent to SAR's WhatsApp. Okay, fine. Now let's go to the next one. Let me run this file. Run this command. Fine. It is done. It is done. Right? If you want to see, we can see it. Let's see one. Data has come, right? Data has come. Somebody can ask, SAR to send to you, right? I think, it can come to your WhatsApp, right? This is a usual model given in Gujarati, right? It was first. Another file is there. Main? I don't know that. Yeah, I'll do it. What is the mail ID? No problem.
N 19
at
Gmail. Yeah.
Yes, the set. Yeah. Yeah, this is the data. The model is this. This is the model. This is the model, right? Yeah, this is the model. Okay, so this is the model. So this is a mileage model, right? You've got a mileage as a function of top speed, engine horsepower, vehicle weight, right? So it is there. MPG in the data set is the mileage, right? SP is the top speed of the car miles per hour. HP is the engine horsepower. WT is the weights, vehicle weights, right? So this is the regression model, right? So this we can run. So data is there. HC1 is that data only, right? You are running it. You are running a model of this kind. Now we have to attach. Now let me, before getting into that, actually let me clear all the data. I've cleared all the data. Yeah. Now I am running the model. So what is the model here? Let me have this, and then I'll just type this. First attach. HC1. I'll just show you it. This is the command I typed. This is the command I had typed. Right? First imported the data. Actually, I got the data into the R. Then I attached the file. Now I am going to type the model. MPG. Let me check. Right? Let me check the data first. Right? So what is there? This is what is seen. So this is the variable, right? This is the variable I have. This is the variable I have. Let me type. So this is the variable. This is the variable. Yeah. MPG, SP, HP, VOL, right? We can write the model based on this, right? What is that? MPG. LM. First, you have to type LM. LM. MPG tilde. What are the variables given here? SP, HP, WT. SP, SP, HP, WT. Okay, so this is it. This is the regression model, right? This is the model. Let me name it as model. So this is my model, right? Let me run it. Then we can write the summary. Right? We can run this thing together. Could you see this? So this is the model. This is the model. So once it is done, I get the model like this. So this is the regression. Mileage is negatively related to speed, right? Positively related to horsepower, negatively related to weight, right? All are significant. All are highly significant. All are highly significant. Right? This is what your results show, right? A linear model, right? R square is 0.8 and F is significant. F is significant. So this is the model status. Now we can test it, right? So I take the help of this one. We have already LM test. So you have to I am not typing anything new, mind you. Bruce Pagan test. Hash, right? Here, what is the model? What is the model here? Model is not LM model, just simply a model, right? Agree? Model here is, right? I named it only model, not LM model, right? So let me run it. Afterwards, you have to print, right? Print the result. Print. Oh, let me paste. Let me give some name for this. BP. This is the name given for this. I'm going to type only this. Of course, you can type everything, but multiple functions can be given in a single line, right? But that will be a big actually a long line, you may have to write. This one is little simpler. I'm going to write up till this point. Let me run it. Yes, the result has come. The result has come. I'll just display it. Yeah, I'll show you how the values are calculated. I'll just BP test. There is a thing. All the LM tests are done with two formulations, right? One is chi-square, the other one is F test. F test formulation is there, chi-square formulation is also there, right? So they are very simple thing, right? Fit are the models. Actually, a model will be specified. That model, right, will be evaluated in terms of chi-square statistics or F statistics, right? So if it is significant, we'll say the model is having a heteroscedasticity problem. Otherwise, it does not have the heteroscedasticity problem, right? I'll show you the model, right? So this is the result. It shows clearly there is a problem, right? Heteroscedasticity problem, right? Because the model is significant, right? The statistics is significant. The statistics is significant. It is very small number, highly significant, right? What is the model, right? In econometrics, right, everything is a model only, right? This is, I told you already how the BP test is run. Yeah. So the BP test, right, here is a chi-square test relating to this model, fit of this model, right? What is the null hypothesis? They have stated this is the null hypothesis. This is the null hypothesis. All the coefficients here equal to 0, right? What do they say? Here they say sigma I square, right? Instead of, that is not possible, right? You cannot do all the combinations of samples and find the variance of it. How would they do it? They would take a proxy. What is the proxy? You know how the residuals are calculated. Residuals are nothing but y minus y hat. Residual is nothing but y minus y hat. Two vectors. Y vector is there, y hat vector is there. Just divide, actually, just difference, you will get u, residual value. Just square it, right? These squared residuals are the proxies for this sigma I square, right? They are the proxies for this sigma I square, proxies for the variance, right? So you will take ui square, the residual square, and you will run a regression on all the independent variables, right? So here, yes, z is the some straight away x's or some functions of x's. So you are taking some x values and you are running a regression ui square on all these independent variables. So that model is evaluated. This is the null hypothesis, right? So this Bruce-Began test is giving the result on that. Bruce-Began test is giving the result on that fit, right? This is a chi-squared version, mind you. This is a chi-squared version, right? This is a fit, like a F test, right? Like the F test for this regression, right? Like the F test in this regression, you are running a chi-squared test on this regression. Chi-square test on this regression, right? This chi-square regression serves the same purpose as F here, right? There in the F test, you are trying to see whether all the coefficients are equal to 0 or not, null model. Here you are trying to check whether these coefficients are equal to 0 or not. Right? Again, this model is checked for the comparison with the null model. Right? If all the alphas are 0, then chi-square will be insignificant. Otherwise, it will be significant. Right? If it is significant, you will have the heteroscedasticity, because heteroscedasticity is not random or is not constant. It is depending on some x values. So that is the change thing. Actually, if it depends on x's, if x changes, the variance will also change. That is the logic. Right? Otherwise, in homoscedasticity, we assume the variance does not change. The variance does not change. Right? It does not change with x's or any other parameter. Right? It is a constant. Here, if the model is significant, we will say it is changing with these variables. Right? So this is how we will interpret the Pushparaj test. Another important thing can be the robust standard errors. Right? The solution for this problem is robust standard errors, or else they will run some generalized least squares, GLS. Right? So there we can see the theoretical discussions. Right? Actually, in the heteroscedastic classes, we will see how this problem can be solved with GLS. Instead of running OLS, people run GLS according to the assumptions on this variation in variance. If this ui square is proportional to xi square, we have to divide the equations by x. Otherwise, if the variance, the ui square is changing in proportion to some other variable, that variable can be divided across, and that is called the weights. The divide means weights. Those weights can be, the weighted regression can be used. So that is the solution. One of the biggest solution for this is the robust standard error. Robust standard error. Right? Actually, this is a remedy. Just look at this. Yeah, I'll just show you. Yeah, this is the, right? If your variance is proportional to xi square, right? You will divide the entire equation by xi, right? You run this regression instead of the original regression. Instead of running this regression, you will run this regression and find the standard errors. This regression will not have a problem of heteroscedasticity, right? This is known as GLS, generalized least squares method, right? So this can also be done with your R, right? So this is the solution. One is you can run either the generalized least squares, otherwise you can run the robust standard error, right? It can address the problem of biased standard error estimations, right? If you correct it, the problem will be solved, right? So as you do for your auto correlation, you can do it for this also. Okay. Now we'll move on to quickly. Actually, Sarosh, can we extend or we can stop here?
So velocity. So
It is done. Yes.
okay, then we can stop here.
Yeah.